Ever wonder how your bank decides if you get that loan? Or how a streaming service just knows what you want to watch next? Well, a lot of the time, the logic behind it is way more intuitive than you'd think. Today, we're going to pull back the curtain on one of the most powerful and surprisingly simple tools in all of machine learning, the decision tree, also known as CART. And that's really the big question, isn't it? Because when you get right down to it, a decision tree algorithm is a master of deduction. It sifts through all the evidence, asks these really targeted questions, and corners the right answer, just like a great detective solving a case. So here's how we're going to crack this case. First, we'll look at the basic idea, what I'm calling the ultimate flowchart. Then we'll figure out how the algorithm asks the smartest questions. After that, we'll see how it measures the mess to know if it's on the right track. We'll also cover how it avoids getting lost in the details. And finally, we'll see the massive impact this thing has had on the real world. All right, let's start at square one. At its absolute core, a decision tree is something you already know how to use. It's basically a flowchart. But trust me, it's a flowchart with some serious superpowers.
I mean, we do this in our heads all the time, right? Is it raining? Yep. Okay, grab an umbrella. Nope. All right, next question. Is it sunny? Yeah, it is. Cool, wear sunglasses. It's just a simple, logical path of yes or no questions that gets you to a final decision. Now just imagine a machine doing that, but with millions of data points and hundreds of possible questions.
And that's where we get the official name, CART. It stands for Classification and Regression Tree. Now, that sounds complicated, but that fancy phrase, binary recursive partitioning, it just means the algorithm takes a huge pile of data and over again splits it into two smaller groups using a simple yes or no question. That's how it builds that tree structure we just saw, but on a massive scale. Okay, so how in the world does the algorithm know which questions to ask? This is where the real detective work kicks in. It can't just ask random stuff, it has to have a strategy to ask the smartest questions, the ones that get it closer to the truth right away. So let's paint a picture here. Imagine all your data is just a room packed with suspects in a mystery. Now the detective's goal isn't to grill every single one of them. No, that's too slow. Instead, the smart detective asks a broad question to split the entire room. Something like, was the person you saw wearing a hat? Everyone who says yes goes to one side of the room, everyone who says no goes to the other. Just like that, you have two smaller, much more manageable groups to deal with. And this whole process is super methodical. The algorithm starts with all the suspects in one big room. We call that the root of the tree. Then it searches high and low for the single best question it can possibly ask to create the most useful split. After it splits the data, it looks at each of those two new groups and does the exact same thing all over again. It's this top-down, one split at a time strategy. But what does best even mean here? How does the algorithm know a good split from a bad one? Well, this is the secret sauce. It actually has a mathematical way to measure the, for lack of a better word, messiness of any group of suspects. See, the goal of every single split, every single question, is to create two new groups that are as pure as possible. And what's a pure group? Well, think back to our detective. A pure group is one where, say, almost all the suspects are innocent or almost all of them are guilty. With every question, you're trying to reduce the uncertainty. So take a look at this. This is a perfectly messy group. It's totally impure. If we're trying to figure something out, a 50-50 mix is the definition of maximum uncertainty. We have no clue what's going on here. Picking one at random is just a coin flip. But after asking one smart question, we might end up with a new group that looks like this. Ah, much better. Now, 90% of the members fall into one category. The uncertainty has plummeted. That is what a successful split looks like. The way the algorithm actually measures this messiness is usually with something called Gini impurity. The easiest way to think about it is as a messiness score that goes from 0 to 0.5. 0 means the group is perfectly pure. Everybody's the same. A score of 0.5 means it's that perfect 50-50 mix, total chaos. So the algorithm's job is to find the one question that causes the biggest drop in that Gini score. Now look, you might also hear people talk about another measure called entropy. For our purposes, they do pretty much the same job. They both measure impurity. The main thing to remember is that Gini is just computationally faster since it avoids some tricky math, so it's usually the default choice. Honestly, in the real world, they tend to build very, very similar trees anyway. Okay, so our detective algorithm is on a roll. It's splitting data left and right, creating pure and pure groups. But this leads to a huge danger in machine learning. What if it goes too far? What if our detective gets a little
obsessed with tiny, irrelevant details. This is a famous problem called overfitting. This quote just nails it. If our detective keeps asking questions until every single suspect is in their own little room, all alone, well, they've perfectly explained the past, but they haven't learned any general rules. The model has basically memorized the data, noise, quirks, and all, and it will completely fall apart the second it sees a new suspect it's never encountered before. So how do we stop this? Well, the most elegant solution is something called cost complexity pruning. And the strategy here is just so clever. First, you let the algorithm go absolutely wild and grow a massive, totally overfitted tree. Then, you go back and you methodically prune or snip off the weakest branches. Those are the ones that add a ton of complexity but give you very little predictive power in return. You end up with a bunch of different sized trees, and then you test them to see which one works best on fresh data.
The other option is to just give the detective a set of rules before they even start the investigation. This is called pre-pruning. You can tell it things like, hey, don't build a tree deeper than 10 levels, or don't even bother splitting a group if it has fewer than 20 suspects. It's faster, for sure, but you do run the risk of stopping the tree just before it finds a really valuable clue.
All right, we've built our tree, we've pruned it to just the right size. So what's the big deal? In our final section, let's look at why this classic algorithm is still a legit superstar in the world of AI and data science.
This is where CART really flexes its muscles. When you put it up against other models, its strengths just pop. The biggest one? CART makes almost no assumptions about what your data looks like. It doesn't need a nice, clean relationship to work. But the killer feature, the one that makes it so valuable in business, is that the output is a flowchart. A real human being can actually look at it, read it, and understand exactly why the model made the decision it did. That is huge. So let's wrap up the key advantages here. Decision trees don't care how your data is shaped. They automatically figure out which variables are the most important all by themselves. They're incredibly easy to explain to your boss, and, maybe most importantly of all, these simple trees are the fundamental building blocks for some of the most powerful and accurate models in modern AI, like random forests and gradient boosting.
And get this isn't some hot new idea. The CART algorithm was first introduced all the way back in 1984. The fact that its core logic is still so incredibly powerful and relevant today, well, that's just a testament to what a brilliant and elegant design it really is. And that really brings us to the final thought. The decision tree teaches us this incredibly powerful lesson. Sometimes the best solutions aren't the most complicated ones. They're the ones that can break down a messy, complex problem into a series of simple, logical steps. So it really makes you think, right? If a simple flowchart can be this smart, what other big problems are out there, just waiting for their own detective algorithm to come along and crack the case?